Ever wondered what sets apart procedural programming from object-oriented programming? Let's dive right in. Procedural programming, as the name suggests, revolves around procedures or functions. These are essentially sequences of computational steps, or instructions if you will, that manipulate data. Procedural programming is like a well-rehearsed orchestra, where each instrument plays its part at the right time, following a strict sequence. It's all about the process, the step-by-step execution of instructions to solve a problem or perform a task. Now let's shift gears and introduce object-oriented programming. If procedural programming is an orchestra, object-oriented programming is more like a jazz ensemble. It's less about the sequence of the play and more about the players themselves, the objects. These objects are like musicians, each with their own unique abilities and traits, but working together to create a harmonious melody. In the world of object-oriented programming, objects are the stars of the show. They encapsulate data and the methods that operate on that data. It's like having a box that not only holds your stuff, but also knows how to organize and manage it. This shift from focusing on procedures to focusing on objects is a significant one. It mirrors the shift in how we approach problem solving in the real world. Instead of focusing on the step-by-step process, we focus on the entities involved and how they interact. This approach makes programming more intuitive and aligns it closer with how we naturally perceive the world. In object-oriented programming, the interaction between objects through well-defined interfaces takes center stage. It's like a conversation where each object, like a person, has a role to play and contributes to the overall discussion. So in essence, while procedural programming structures the program around procedures or functions, object-oriented programming structures the program around objects. And that's what sets these two programming paradigms apart. Now, let's delve into the core principles of object-oriented programming, starting with data abstraction. Imagine you're behind the wheel of a car. You know how to start the engine, steer the vehicle, and slam on the brakes when a squirrel darts across the road. But do you need to understand the intricate mechanics of the combustion engine or the hydraulic systems that make these actions possible? Certainly not. You're interacting with an abstraction of the car, utilizing its key functions without getting bogged down in the gritty details. This is the essence of data abstraction in object-oriented programming. In the realm of coding, data abstraction is all about hiding the internal workings of a class, while exposing only the necessary functionalities. It's like a magician's trick. You're dazzled by the end result, but the actual sleight of hand remains a mystery. Let's consider a real-world example, a car object in a programming context. A car has many intricacies, the engine, the gearbox, the electrical systems, to name just a few. But when interacting with a car object in our code, we don't need to worry about these complexities. We're provided with simple methods like start and stop. We can start the car, we can stop the car, but we don't need to know how the spark plugs ignite the fuel or how the braking system engages. The beauty of data abstraction lies in its simplicity. It allows us to use objects effectively without getting lost in the details of their inner workings. It's a layer of protection that keeps the complex mechanisms hidden, allowing programmers to focus on the broader picture. In essence, data abstraction is the principle that enables us to drive cars, use smartphones, and interact with all kinds of complex systems without needing a PhD in engineering. It's the magic that makes the complex simple, the unfamiliar familiar, and the daunting doable. Data abstraction, therefore, allows us to focus on what an object does instead of how it does it. Moving on, let's explore the principle of inheritance. Inheritance is akin to the genetic inheritance we observe in the natural world. In the realm of object-oriented programming, it allows a class, say child, to inherit properties and behaviors from another class, referred to as the parent. This leads to a fascinating hierarchical relationship between classes, much like a family tree. Now, let's illustrate this with a simple example. Imagine we have a generic class called vehicle. This class could have properties like speed or weight, and behaviors like move or stop. Now, we create a more specific class, car. By using inheritance, the car class can inherit all the properties and behaviors from the vehicle class. In addition to this, the car class can have its own unique properties and methods, like number of doors or convertible roof. Inheritance, therefore, not only promotes code reuse, but also helps us establish a logical, hierarchical relationship among classes. Next up, we have the concept of polymorphism. This principle is all about versatility and flexibility in the world of object-oriented programming. In essence, polymorphism allows objects to take on multiple forms. It's like a shapeshifter in a fantasy novel, where one entity can transform into different forms based on the situation. But how does this translate to programming? Let's imagine we have a superclass called shape. This superclass has subclasses like circle and square. Each of these subclasses has its own version of a method called calculate area. Despite having the same method name, the calculate area method works differently in the circle and square subclasses, fitting to their unique characteristics. This is polymorphism in action, same method name, different implementations depending on the object. Polymorphism not only gives objects the ability to take on many forms, but it also enhances code flexibility and readability. It allows us to write more intuitive and adaptable code, making our programming lives a whole lot easier. Polymorphism, as you see, gives objects the flexibility to take on many forms, enhancing code flexibility and readability. Last on our list of OOP principles is encapsulation. Now, encapsulation is all about bundling data and the methods that operate on that data into one single unit. In other words, an object. It's like packing a box. You put related items together and seal it up. This box is your object, and inside it, you've got your data and the methods that work with this data. Let's take the example of a bank account object. The data here would be the account balance, and the methods might be deposit and withdraw. Encapsulation means that the account balance is bundled together with these methods into the bank account object. This does two things. First, it promotes modularity. You can move this bank account object around in your code as one unit. Second, it hides information. Outside code can't directly access the balance. It has to use the deposit or withdraw methods. Encapsulation therefore enhances code maintainability and security by bundling related data and methods into a single unit. Having covered the core OOP principles, let's now shift our focus to Java. Java, as many of you may know, is a popular high-level, object-oriented programming language developed by Sun Microsystems. It's widely used for developing robust and secure applications and applets that can run on any platform supporting Java. Delving into the world of Java, we find two main types of programs: applications and applets. A Java application is a standalone program that runs directly on your computer. Think of it like your favorite game or word processor. On the other hand, a Java applet is a small application that runs within a web page, providing interactive features that can enhance your browsing experience. Now let's peek into the Java compilation process, which is a bit unique. When you write Java code, you're essentially writing what's known as source code. This source code is then compiled into something called bytecode. This bytecode is a platform-independent code that can be run on any machine, provided it has a Java virtual machine or JVM. The JVM translates the bytecode into object code, which is the machine language that your computer understands and can execute. This two-step process from source code to bytecode to object code is what gives Java its famed platform independence. And speaking of platform independence, it's one of the key features that sets Java apart. No matter what operating system you're using, be it Windows, Mac OS, Linux, or anything else, if it has a JVM, it can run Java programs. But that's not all. Java is also known for its simplicity, making it a great language for beginners and experts alike. It's robust, meaning it's designed to avoid crashes and data corruption. And it's secure, with built-in mechanisms to protect against various types of attacks. So there you have it. Java, with its simplicity, robustness, security, and platform independence, indeed stands out as a powerful tool in the realm of object-oriented programming. Let's take a moment to review what we've covered today. We've journeyed from the procedural to the object-oriented programming paradigm, seeing how the focus shifts from procedures to encapsulating data within objects. We've delved into the four core principles of object-oriented programming. Firstly, data abstraction, where we conceal the complexities of a class, exposing only the necessary functions. Secondly, inheritance, which allows a class to inherit properties and behaviors from another, promoting code reuse. Thirdly, polymorphism, enabling objects to take on multiple forms for increased flexibility. And finally, encapsulation, the bundling of data and methods into a single unit for better maintainability and security. Then we ventured into the realm of Java, understanding its different program types, the compilation process, and its unique features such as simplicity, robustness, security, and platform independence. Understanding these concepts forms the foundation for your journey into the world of object-oriented programming and Java. Keep exploring, keep learning,